Hi, anyone. I will talk about metric inequalities with positive scalar curvature for asymptotically Euclidean spin manifolds with boundary. As an application, I will discuss a localized version of the positive mass theorem. In the first part, I will recall the notion of an asymptotically Euclidean end and of the ADM mass. In the second part, I will discuss a localized version of the positive mass theorem. And in the third part, I will present the main metric inequalities that I proved together with Rudolf Zeidler in the spin setting. And finally, in the fourth part, I will give a sketch of the proof. For a Riemannian manifold M, let me recall you that the scalar curvature is a smooth scalar valued function that is constructed out of the Riemann curvature tensor. It is the trace of the Ricci tensor, and it is the weakest curvature invariant that can be attached, at least pointwise, to a Riemannian manifold M. The study of manifolds of positive scalar curvature has deep ramifications in both differential geometry and general relativity. There are two main methods for investigating this topic. So the first method is the Dirac operator method. It was initiated by Lichner-Horowitz, Atiyah, and Singer, and makes use of the properties of the spinor Dirac operator. The main restriction is that it applies only to spin manifolds, or at least to manifolds which admit a spin color. The second method is the minimal hypersurface method. This was initiated by Schoen and Yao, and is based on the spectral properties of the conformal Laplacian on a stable minimal hypersurface. Its main limitation is that it requires the dimension of the manifold to be at most 7. This dimensional restriction has been recently removed by Schoen and Yao, at least in some situations. One of the main achievements of the study of manifolds of positive scalar curvature is the proof of the positive mass theorem that I will now review. We start with recalling the notion of an asymptotically Euclidean manifold. So let M be a smooth n-dimensional Riemannian manifold. We say that an open set E is an asymptotically Euclidean end of order tau, where tau is greater than n minus 2 over 2, if, well, first, the scalar curvature is in L1 on E, and the second condition is that there exists a diffeomorphism phi between E and the Euclidean space minus a disk, and such that the pullback metric converges to the Euclidean metric with a certain decay, which is expressed by saying that the difference belongs to this weighted C2 space. Now, we say that that the Riemannian manifold MG is asymptotically Euclidean if there exists a bounded set K such that M minus K is a finite union of asymptotically Euclidean ends. Note that once we fix such a diffeomorphism phi, then we have corresponding asymptotically Euclidean coordinates, x1, xn, and we have a radial coordinate. So here I draw a picture of a asymptotically Euclidean manifold MG with 3 ends, E1, E2, and E3. We now move to the notion of ADM mass. So the ADM mass of a asymptotically Euclidean end E, which we denote by the symbol, is defined as this limit. So here, omega m minus 1 is the volume of the unit m minus 1 sphere, and S m minus 1 r is the sphere of radius r with respect to the chosen asymptotically Euclidean coordinates. And of course, ds is the volume element on Sm minus 1 r, which is induced by the Euclidean background metric. Note that this limit exists and is independent of the chosen asymptotic coordinates by foundational results of Bartnik. We now state the positive mass theorem. So suppose that Mg is a complete asymptotically Euclidean Riemannian manifold without boundary of dimension at least 3, which has non-negative scalar curvature. And then the ADM mass of each end of M is non-negative as well. And moreover, there is a rigidity part stating that if M has an end of 0 mass, then M is isometric to the Euclidean space. Now, this theorem was first proved by Shene Yao in dimension at most 7 using the minimal hypersurface method. The higher dimensional case was treated again by Shene Yao in a recent preprint. In the case when M is spin, the positive mass theorem was proved by Witten using the Dirac method. So in this case, you have no dimensional restriction, but of course, you require the manifold to be spinned. Note that the ADM mass of a single end is defined by computing a certain limit of a quantity which is defined within the end itself. And therefore, it is natural to ask to which extent the positive mass theorem can be localized. So in other words, in this talk, I want to discuss the following question. So suppose that M is a not necessarily complete Riemannian manifold without boundary, and suppose that E is an asymptotically Euclidean end. Now, which conditions on the metric G would imply that the ADM mass must be non-negative? So the condition that the scalar curvature is non-negative is not enough to conclude that the ADM mass must be non-negative as well. To see this, just consider the Schwarzschild space on negative mass. So in this case, we have a incomplete metric of that is scalar flat with negative mass.